Hello grade 9s, this is Mr. Miller, and welcome to lesson 7.1 on multiplying and dividing monomials. So before we begin this lesson, let's just take a look at all of the algebra tiles that we have here and what they are representing. The first one is the positive x tile. So with tiles, you can always tell that they're positive because if they're in black and white, they're shaded. If they are white, then they are negative. So this is an x tile. It's x units long and it's 1 unit wide. That's what it looks like in black and white. In your textbook, you're going to see it in color, and it will be green. And here's the negative version of that. This is the negative x tile. It's x by 1, but it's got a negative value to it. So it looks white on photocopied handouts, and it will be white as well in the textbook. Looking at the positive x squared tile, the positive x squared tile is x units long and it's x units wide. It's shaded in so you know it's positive. In the textbook, that tile will be green. Here's the negative version of it, so it's white. Of course, in the textbook it will be white as well. Next we have the positive y tile, which is y units long and 1 unit wide. It's shaded in so it's positive. And in the textbook, that will be orange. Next we have the xy tile, and it is x units long and it's y units wide. Here it's shaded so you can tell it's positive. And this is what it looks like in the textbook. Also gray. So these are the algebra tiles, and what you can see is that their areas are really their values. Okay, so this has an area of x squared because it's x times x, and that's the value of the tile is x squared. This is y by 1, and it's y times 1 would be just y, so that's the value of this y tile, and so on. So now we're going to use these algebra tiles to help us understand in a pictorial way about algebra. So the first thing we're going to look at here is to write a monomial multiplication statement for each set of algebra tiles. So you can see that we have a length and a width here. Let's write down what each one of those is. So here you can see that we have a 2x for the length, and here we have a negative 2x for the width. And I say negative 2x because these ones are white. So when we multiply the positive 2x by the negative 2x, you can see that we get negative 4x squared. So that's because there are 4 of these negative x squared tiles. You can look at these individually. You can see how they're lined up, that an x times a negative x gives you a negative x squared, and x times another negative x gives you another negative x squared, and so on. That gives us all 4 of these negative x squared tiles. So, and if it helps you to remember, you can write the multiplication symbol here. This is a multiplication that we're doing. Next, we have the length being 3x, and the width here is 2y. So when we multiply the length, 3x, by the width, 2y, we get an area of 1, 2, 3, 4, 5, 6 of these tiles, and these are x, y tiles. So now you can see how we're using these tiles to model multiplication of monomials. Next, we'd like to take some monomial multiplication statements and represent them with a model, and we'll use that to determine each product. The first one we're going to do is negative 3x times negative 2x. Let's set that up. All right, here we've set up a length of negative 3x, and here we've set up a width of negative 2x. Next, we want to actually determine this product, so we need to figure out what this length and this width gives us in terms of area in here. Let's fit in some algebra tiles that will take up this area. And here it is. Notice how that when we have a negative x times a negative x, it gives us a positive x squared. And here we have 6 of them. So the product is positive 6x squared. Of course, once you get used to this, you're not going to need to use these tiles anymore. Probably can recognize the fact that all we're doing here is multiplying the number negative 3 with the number negative 2 to give us the positive 6. And the x times the x is what's giving us the x squared. But for some people, maybe this pictorial representation gives them something a little bit more concrete to visualize. Let's take a look at the next monomial multiplication statement. We're going to set up x times 4x. So again, just like the last one, which was a multiplication, here we have another multiplication where the length is 4x across here, and the width is x. And when we multiply these two things, that will give us this area. Let's fill it in now. And as you can see, every x times x is x squared, so we have a total area here of 4x squared. So the product in this case is equal to 4x squared. Of course, moving beyond just using tiles to figure this out, you can recognize that the coefficient here is 1, so we're doing 1 times 4, which gives us 4, and x times x gives us x squared. Now moving on to number 3, we want to determine the product of each pair of monomials, and there are no diagrams necessary. So let's simply do the coefficient times the coefficient, which is negative 8, and x times x, which gives us x squared. Again, 3 times 7 gives us 21, and y times y gives us y squared. 5 times negative 3, that's negative 15, and x times y is simply xy. 6 times negative 0.2 is negative 1.2, and m times m is m squared. Finally, if we do 2/3 times 12, that gives us 8. So if you did 2 times 12, that's 24, divided by 3, that's 8, or you could do 12 divided by 3, that's 4, times 2 is 8. In any case, it gives you the same result. N times n is n squared. So now let's move on to the next page. We want to write a monomial division statement for each set of algebra tiles. So what you can see here is that there's a product that's already given if this were a multiplication. And you can see that we've got the 4x squared tiles in the middle here. And what we're dividing by, so this is the dividend, and we're dividing by, the divisor is indicated up here. We're dividing by 2x. So we've got 4x squared that we're dividing by 2x, or you could alternatively write it this way as 4x squared divided by 2x this way. And by the way, I put the brackets just to make it clear that I'm not just dividing by 2, but I'm dividing by 2x. And of course, the result is, it's kind of like you're looking for what is this width that when multiplied by that length gives us this area. And of course, you probably can figure that out, that that would be 2x. But to distinguish this question from our multiplication, we don't actually we don't draw in the quotient here. Just leave it as a question mark. So likewise here, you can see that what we've got is we've got 6 of a certain kind of tile, and this particular tile, these are negative x squared tiles. So this is negative 6x squared, and we are dividing by 3x. And so this quotient can also be written in this way, negative 6x squared over 3x. And now we just need to figure out what is that width that when we multiply by this length would give us this particular area. So first of all, you have to recognize that it takes a negative to multiply a positive in order to get a negative product. So we know that it's going to be negative something. And we can see that it's 2 tiles wide, and it's 2x tiles wide. Now, of course, we do want to move beyond the tiles. So you'll probably recognize that in each case here, we were able to get our answers by taking the coefficient and dividing by the coefficient. So 4 divided by 2 gave us 2. Just like here, negative 6 divided by 3 gave us negative 2. And x squared divided by x is x. Just like here, x squared divided by x is x. But we're going to practice just setting up a division statement with a model, and we're going to determine a quotient. So the first one we're going to do is 8x squared divided by 4x. So here we have the 8x squared that we're dividing by 4x, and we're looking for a quotient here. We're looking for a width that when we multiply this particular width by the length 4x, we'll end up with 8x squared. And of course you can see that it's going to take 2x tiles to do that job. Plus we can also see that 8 divided by 4 is 2, and x squared divided by x is x. Let's take a look at the next one, part B. We want to represent 6xy divided by 3y. Let's do that now. Here it is. I've got my 6xy tiles, and I'm dividing by 3y, and I'm looking for a quotient here. I'm looking for a width that when I multiply by this length, 3y, it's going to give me this particular area. Now it's very important that you get the arrangement right here. I wouldn't want to stack these xy tiles, these last two, down here. I want to arrange them so that I've got 3y across, and then I'll be able to figure out what the width is. And you've probably figured that out by now, that it is 2x in width. So you can figure this out a number of ways. First of all, by actually placing 2x tiles down here and recognizing that that takes up the width. You can also recognize just from the expressions that 6 divided by 3 is 2, and with xy divided by y, that will leave you with x. The factor of y simply divides out. So now, if you've got a good understanding of that, hopefully now you'll be able to move on to determine quotients without having to do the diagrams. 16x squared divided by a negative 8x can simply be done by doing 16 divided by a negative 8, which is negative 2, and x squared divided by x, which is just x. And then in part B, we've got 15 divided by 3, which is 5, and xy divided by y, which leaves us with just x. And so on. If you get the idea, you may want to pause the video right now, try the next 3 on your own, then play it when you're ready to go. So in the interest of saving time, I've skipped straight to the answers. You can check against the ones that you've tried to do on your own. First one is simply 3 because both the factors of m and n divide out. The next one can be represented in a few different ways. The 12 over 8 is a fraction which reduces to, in lowest terms, 3 over 2. And whether you write this as 3 over 2 times y, or 3 times y over 2, or 3 divided by 2 is just 1.5, so 1.5y, it's all the same. With part E, again, there's nothing wrong with decimals. We can certainly have our answer, our coefficient here as a decimal, negative 7.1, and m squared divided by m is simply m. So next we'd like to try to do some different kind of problems. It says here that we've got a triangle that has a base of 12x centimeters and a height of 3.4 times x centimeters. We want to know what is the area of the triangle. So let's draw a quick sketch of this. So we're told that the base is 12 times some unknown amount of centimeters, and we know that the height is 3.4 times the same unknown amount of centimeters. We'd like to know what is the area. So to find the area of a triangle, you do base times height and then we divide by 2. So 12 times 3.4 is equal to 40.8, and x times x is x squared. We do have to divide by 2, so that would give us 20.4 x squared, and the units would be centimeters squared. So that's an example of a multiplication of polynomials type of question. Next, we'd like to look at a question where we're going to be dealing with division. We're told that the area of a parallelogram is 25.6 x squared meters squared. We want to determine the height if the base is 8x meters long. So just doing a rough sketch of this parallelogram, it would look something like this. So we are told that the base is 8x, and we're told that the area is equal to 25.6 x squared. The length is measured in meters, the area is measured in meters squared. We need to figure out what is the height. So it helps to know that for a parallelogram, that the area is base times height. So in order to get the height, we simply need to take the area and divide by the base. So that is 25.6 x squared divided by 8x. So first of all, the 25.6 divided by 8 is equal to 3.2, and x squared divided by x is simply x. The units for measuring the length of the height would be in meters. And there you have it, folks. That's the end of this lesson. Thank you for watching, and have yourselves a wonderful day. Bye-bye.